we're going to figure out the string by treating a small curved segment. So instead of the whole string, let's think of a little piece, but let's go ahead and keep it on the same axes, plus y here, and plus x here. And let's imagine a little piece that, I don't know, maybe kind of looks like that. Doing something like that. There's our little piece. This side is at a position we'll call x. This side is a position we'll call x plus delta x. Okay? So it's a differential piece, or a small piece of the string. What we're going to do then is apply the laws of physics and to describe the motion of that piece of the string. And the only law of physics we need is Newton's second law. Sum of the forces equals ma. That's really all we're going to do. Okay? So let's think about the force on this string. We're ignoring gravity. Gravity makes it sag. Let's not worry about that. It doesn't sag much. The force we want to think about is the tension. Right? The string is under tension, and tension is always along the direction of the string. So it's interesting when the string is curved, because then the tension isn't along the exact opposite direction. Right? When the string is straight, the tensions just cancel. But when the string is curved, they don't quite cancel. Okay? So that's what we're going to work with. Now, another parameter we want to think about is the angle. So if we think about the direction of this tension, here it's at one angle, and here it's at a different angle. So we're going to call this one at theta, and we're going to say this one is at theta plus delta theta. So the string is at theta, angle theta at x, it's at theta plus delta theta at x plus delta x. And we're just sort of repositioning the origin of the angle for each side. Okay, we could do it absolute, always in terms of this being 0, but it's easier just to reorient it. Okay? So if we have that, now let's write that rule down. So the tension is constant, magnitude, but changing direction. There you go. Okay, so now all we got to do is apply F equals ma. Sum of the forces equals ma to each direction. So sum of the forces in the x equals m times the acceleration in the x. Let's see, let's do that first. So sum of the forces in the x, well, in the forward direction, we have the tension, and this component in the x direction is just the tension times the cosine of that angle. So we have t times the cosine of theta plus delta theta. And in the negative x direction, we have t times the cosine of theta. Right? Minus t times the cosine of theta equals m. And then in this case, we're talking, oh, let's not worry about the other side yet. We're just doing the forces. Okay, sum of the forces in the x. All right, let's get the sum of the forces on the y. And it's very similar. When we look in the y direction, we care about this component up and that component down. So up, we have t sine theta plus delta theta. And then down, we have t sine theta. All right? So there's our forces. Now, we are only going to solve the motion of the string. So for small thetas and delta thetas, okay? Basically small angles. Not only small changes in angle, but small angles everywhere. So the change can't be big, because even the angle can't be big. We're talking about small perturbations of the string, okay? And if we say that, then the cosine of theta plus delta theta is roughly equal to 1. Right? So small angle approximation typically tells you that the sine of the angle is about equal to the angle itself if it's small, and the cosine is about equal to 1. You can see that if you look at a plot of sine and cosine. Right? Cosine around 0 is at 1, and it has no slope. It's pretty much 1. And sine around 0 is like a line around the origin, right around 0. So that's why for small angles, that's how they behave. So if the cosine is roughly 1, and also the cosine of theta is roughly 1, and theta plus d theta is roughly 1, if they're both 1, then the force in the x is 0. Right? So the sum of the forces in the x approximately is 0. So what this is telling us is for the behavior we're thinking about, the thing never moves this way. We're just thinking about the piece of the string moving up and down. Okay? Now, for the sine theta, though, that's where it gets a little tricky to think about here. Sine theta for the small angles, right? So we're talking about small angles, roughly equals a lot of things. I'm just going to write them down, and then we'll talk about it. Okay? Sine theta for small angles roughly equals sine theta over cosine theta, right? That's legal, because this is small, and cosine theta is just 1 anyway, so you can divide it by 1. It's still true. And if it's sine over cosine, it's roughly equal to tangent theta. Right? Because we know sine, tangent, sine over cosine. For small angles, tangent theta, sine theta are about the same. Plot them together and look right near the origin. They're both just kind of going up with a slope of 1. That's also, we know the tangent, if you think about it, is kind of like the rise over the run, or it's kind of like the slope, right? Or if you think about derivatives, it's like dy dx. I'll write it as a partial since we're doing a string. For small angles describing a string this way, all those are true. This little angle is roughly telling you what the slope is. Okay? It's the rise, it's really the rise where the run would be 1 for small angles. So anywhere we've written sine theta, we could replace it with really any of these, but we're going to replace it with this. It's telling us that's the slope, therefore that's the partial derivative, which really, in terms of y and x, is just the slope. dy dt is a velocity, but dy dx is a slope. So that's what we're going to use.